This is episode 2 of my autonomous solar rover video series. In the last video, the tiny little gearboxes I was using failed.
Oh yeah, definitely stripped gears.
And I started looking for alternatives. I found these brushed Barbie Jeep motors that were just a bit too fast, so I thought it would be fun to design a 3D printable cycloidal speed reducer to plop on the output.
That is real cool.
Now I know a cycloidal gearbox is probably not the optimal choice of speed reducer for this application, but I thought designing a cycloidal drive for the Rover would be a fun way to push 3D printed parts to their limits and see what they can really withstand. The design I came up with has a 13:1 ratio and easily mounts to the Barbie Jeep gear motor. Here's the build compilation. I printed everything on my stock CR10. These ring bearings are a crucial part of the design. They allow for thick 3D printed shafts with off-center lobes that make the cycloidal discs do their oscillating thing and roll around the outer gear. This blue thing is the mount that holds the gearbox onto the Barbie Jeep motor. Using this blue PLA was a fatal mistake. You'll see why later. Assembling everything is a bit tricky because it all has to line up just right. There it is working without the output spline installed. I used long M5 bolts that stick into the cycloidal discs and transfer power out of the gearbox and into the wheels. Here's putting bearings on the output splines. I didn't end up having enough bearings for all the gearboxes, so I ended up using 3D printed bushings on some of them. The neon things on the ends are just little nuts that hold the bearings in place. I used petroleum jelly as lube, which seemed to work great. I just heated it up and poured it in there. This design is nice because it's fully enclosed to keep debris out of the cycloids. Attaching it to the gear motor is pretty easy. You just plop it on there and screw a retaining bracket on the back to hold it on. I then cut off my old bolt axles and replaced them with 12mm bearing rod. The gearbox assemblies then just slide on over that. I decided to 3D print the wheels all in one piece, which probably wasn't a good idea at first. I sprayed some clear coat on them to give them a bit more protection and bolted them onto the Rover. This is the battery I made from a bunch of cells that I harvested from some dead drone batteries. I soldered 6 of them together into a 3S2P pack that's 32 amp hours, so quite a bit of capacity. This video is sponsored by PCBWay, a full-service and custom PCB prototyping service. They offer instant quotes, quick-turn fabrication, low-volume production, and more. Check them out at PCBWay.com.
So this is my first time bringing the Rover to the test field since its drivetrain upgrade, or it might be a downgrade. I'm not really sure yet at this point in time, but it seems to be working okay so far. So I'm just gonna wait around for a while and kind of observe it and see if it seems to be tracking on its waypoint mission very well. I've been tweaking some parameters. It's definitely a bit faster now, but I have a controllable DC to DC on these motor drives, so I can turn down the voltage a little bit and limit its max speed. Oh, rats. I guess it has enough torque to sometimes just articulate itself in half when it's turning too sharply. I actually had zip ties around here, so it wasn't supposed to be able to do that, but it looks like it broke the zip ties off. Thing's got a lot of torque. This thing is not in good shape. I also realized that this gearbox is kind of broken. This blue piece here that keeps the whole cycloidal housing from rotating, that broke off, which is crazy because it would take so much torque to break that piece off. I also put some beefier zip ties right here, so hopefully it won't fold itself in half again. I think I'm gonna shorten the wheelbase of the whole thing too. Right now the axles are mounted kind of at the edge of the frame, like, you know, on the front and back of the frame, but I'm gonna move them in a little bit so that they're under the frame more. The whole thing will get a little bit taller, but it'll have a shorter wheelbase, so it should be able to turn a lot better. It's definitely not healthy. but it only ever tries to do that when it's doing a full 180-degree turn. This is so unfortunate. Despite having driven out here successfully for several days, within 5 minutes of getting out here today, the wheel breaks off. So it's a new day. I've got 2 new wheels on this side. The plastic is much thicker. The wall thickness is 2 lines, not just 1, with a 0.8mm nozzle, and the design is just more robust in general. So far those seem to be working really well. But I do think that these old ones are not going to last very much longer, so it's only a matter of time before they shatter. I've got a new Genasun MPPT charge controller installed. This is the GV10, and I think it's a lot more efficient and it just works better overall than the last cheap Chinese charge controller I was using. I also recalibrated the compass, which has it running waypoint missions a little bit better now. So I'm going to let it do its thing and come back later. This rear wheel right here stalls really, oh yeah, look at that. It sheared the spline off on that rear right wheel. Once I took the wheel off, I realized the entire cycloidal pin holder with the bolts that fit into each one of those holes, it just broke apart and fell off, I guess. So this is interesting. This is the first actual failure of the cycloidal gearbox. And I'm assuming it was because that piece was made out of super brittle, like crappy blue PLA. Like you can see cracks all along these parts. Just from that brittle PLA. All this other PLA that's not blue has been holding up really well, but that stuff, it was really bad, so that's probably why this part failed. So I've now replaced all the old brittle wheels with these new, more robust 3D printed wheels, but everything in the cycloidal gearbox is the same. I had to change out a few of the output spline parts because they were made out of that super brittle plastic. But other than that, everything is the same. The cycloids are the same. The bearings that rotate around through the inside of the cycloids are the same. So I'm just gonna keep running this thing until some fundamental parts in the cycloidal drive starts to break. This thing has been left unattended in the field for like 4 days. I just pulled up to find it still running. That is so satisfying. So this goes to show that on a partly sunny day, it will get enough power from the sun to boot up and start running. So I am very happy. This is great. So the Arduino that controls the flight mode has it in hold mode right now. And then once the voltage gets high enough in a few seconds, oh, there it goes. Once the voltage gets high enough again, it starts driving. So it's just kind of on and off, borderline being charged enough. But it's also partly cloudy, so on a sunny day it might do a lot better. No, don't hit the car. Oh my God, that thing's got so much torque. Okay, hopefully it's still running in 4 more days. Bye. So we're probably at about 3 weeks now, and it's still going strong. With direct sun, it's probably on for about 50% of the time, and just off charging for probably 50% of the time. So that means it's getting 50% of its energy that it needs from the sun, and the battery is just kind of living at its low voltage threshold. It seems to drive for about a minute before it charges again. So it's just kind of every other minute, on and off, on and off. But I still can't believe that mechanically everything is working well. It's pretty amazing. So over here, I've got the EcoFlow Delta 1300. It's basically just a big tub full of lithium ion cells. It's just a giant power bank. On one side, you've got a bunch of AC power outlets. And on the other side, you've got a bunch of USB connectors like USB-C and USB-A. And you can charge it off the wall pretty quickly, or you can charge it off solar like I'm doing here. If we look at the little screen on the side, it looks like I'm doing about 80 watts right now. It's at 88% full. So I'm gonna charge this up a bit more and then try and cook a burger on it with the George Foreman. So we will plug this in. The screen is saying that it's outputting 772 watts. So the battery's at 88% right now. We'll see if it has enough juice to cook my burger. It's gonna be good. We've got Rovers driving with solar power. We got burgers cooking with solar power. This is what it's all about. Okay, I think it's pretty done at this point. So if we look over here on the battery percentage thing, we're at 81%. Huh, so I could cook a lot of burgers on this battery. Woo-wee.
Oh, that was hot. Oh, that was a hot burger. That was really good though.
The Rover's driving a lot today. Probably over a 50% duty cycle, I'd say. Oh, it's sounding a little crunchy. Oh, wow. It looks like this motor might be broken. It's trying to skid steer. This motor's not working. Huh. We might have had a failure. It's 3 days after the last time I was out here. It still seems to be moving pretty well. It's just that one motor might be out. Let's see if I stop it. It's still got torque, so it's still getting torqued, but just not a lot for some reason. I hear a lot of crunches, so that's a little concerning, but it seems to be working well enough, so I'll just let it keep doing its thing. Ah! Stop, stop, stop. And this is just running over pieces of its own gearboxes. Wow, here's another bolt. I found 2 of these so far. Getting a lot of my oh, 3 of them. That must have been what you just heard. Oh, look, 4 of them. This thing is just dropping a trail of PLA shrapnel. Which gearbox just exploded? Oh wow, I think 2 of the gearboxes have exploded. Wow, it's pretty crazy. This thing has been out here alone for so long, and while I'm here, it just exploded. That's so random. There are even chunks of PLA in front of the Rover though, so that means that it's been dropping little chunks for a few laps. Looks like this gearbox is fine. That might have a chunk out of its spline. Oh yeah, there's some chunks out of that spline in there. This one looks all fine and dandy. And then this one also doesn't look very healthy. So it's just the 2 on the left side that are missing some things. But it's still driving. It never used to go backwards, so that's it trying to skid steer. But the side that normally would be driving forwards right now is not working. So I think this thing is done. It needs a gearbox upgrade. Going the wrong way.
Again, thank you to PCBWay for sponsoring this video. Have you ever wanted to make your electronics projects look more professional? Or are you a small business that needs low-cost, quick-turn PCB fabrication? If so, check them out at PCBWay.com. Their website has an instant quote feature, so you can get started fast. Also, check out this great video on how PCB manufacturing works. Thanks again to PCBWay. So this is what it looks like after taking the wheel off. Basically, this blue part was printed out of that really crappy, brittle blue PLA, and it just kind of shattered, and that was the case on both of these wheels that failed. It looks like the cycloidal discs and everything in there are still more or less fine. It looks like there was some damage there on the edges of the cycloidal discs because the blue thing broke and those bolts got all twisted sideways probably, and then really scuffed up those cycloidal discs. But other than that one blue part, it seems like everything else was in pretty good shape. So I'm wishing I would have switched these blue parts out the last time I rebuilt these cycloidal gearboxes. If that were the case, it would probably still be going. So this lid is made out of that super brittle PLA, and it has some cracks in it, like right here, but that doesn't, oh, there it goes.
So I've upgraded the drivetrain on the Rover, but I still want to see how long these cycloidal gearboxes will really last, or at least the ones that don't have brittle blue PLA parts. So I'm cycle testing the remaining 2 cycloidal gearboxes by having them just lift up a gallon of water and a bike lock over and over again. And I'm just gonna let this thing run until it breaks, basically. So I'll start the timer.
Wow, that metal shaft sheared off. Crazy. It's at almost 500 hours.
So this has been running for 500 hours at this point, and it just won't break. So I'm gonna take it apart now and see what's inside. Here we go, moment of truth. Huh, doesn't look bad at all. Ah, so this one, this one only had 1 set of bearings, and the rest of the posts were just PLA. Oh wow, I can definitely tell that the inner diameters of these little PLA bushings definitely wore down a lot. That's probably where a lot of the backlash was coming from.
There's still quite a bit of petroleum jelly everywhere, so it's still lubricated. And these cycloidal discs look fine, really. I kind of expected them to get like enlarged, as those things were just circling around inside there the whole time it was operating, but looks fine. So based on the wear and tear, I bet this thing would run for a lot longer. I think the first thing to go would probably be the little PLA bushing posts, but since one of those was made out of steel bearings, it would probably still keep going and still keep operating for quite a while. So I'm glad I didn't keep doing lifetime testing with this, because it would have just taken way too long. Well, that was fun to play around with, but the Rover must keep driving. And I'm not a huge fan of these brushed gear motors just because they're not that efficient. And I don't have really high control fidelity with the brushed motor drives I'm using. So it's time to upgrade the Rover again. Got some new gearboxes over there. That was just a sneak peek. I'm not going to talk about that anymore until the next video. So stay tuned. Thanks for watching. Bye. So here's some footage from before the cycloidal gearboxes that I forgot to put in the first Rover video. It's an explanation of how the electronics are set up. So I figured I'd do an overview of the electronics before I put everything in a Tupperware for waterproofing. But basically we have the flight controller over here. It's a Pixhawk 4, and connected to that is the GPS out here on a mast to get it away from all the steel that interferes with the compass. And then we also have the telemetry radio that's connected to that. Once this thing is running autonomously though, I'll probably unplug this to save power. This is the power distribution board. The MPPT solar charge controller is going to plug in right here. And this basically just gives a 5-volt output to the flight controller. It also measures the voltage and current and sends that data to the flight controller. And it also splits out the motor signal. This big power distribution board isn't super necessary because I'm using a 4-in-1 ESC. Usually these are used when you have 4 different ESCs and you need to distribute power and signal to all of them. But it came with the flight controller, so I threw it on there just for the voltage and current sensing. But anyways, then over here, like I said, there's a 4-in-1 speed controller. I potted that in epoxy. I think it's a multi-star branded one. And then of course all the phase wires going out to the motors. It's kind of a rat's nest. Here's where things get interesting. This port here is the RC signal input on the Pixhawk 4 flight controller. And that is connected to this little device called an S2PW. Basically what this does is it takes PWM inputs. A PWM signal is basically just a servo signal. So it takes servo signals and converts them into S-bus. And then it sends that S-bus signal out here and into the flight controller. And this thing is getting the PWM signals from an Arduino Nano. And I wrote some code for this that basically measures the battery voltage with a voltage divider right here. And based on the battery voltage, it sends a signal that goes through here and then into here to put the flight controller into auto mode, which makes it run the waypoint mission. So basically, when the battery voltage gets below a certain threshold, it'll stop the waypoint mission and just sit there. And then when the battery charges back up from the solar power and gets above a certain threshold, this will start the mission again. And then over here I just have another relay that I could eventually run an accessory off of that will turn on and off as it goes in and out of auto mode. So that could be for converting it into a lawnmower in the future or something like that. And then over here we have the MPPT charge controller. This is just a cheap like $20 one from the internet. It's made for 3-cell lithium batteries, which is what I'm going to be using. So I'm going to probably mount that up here underneath the solar panel so that it stays dry, and then I won't need to enclose it in anything. So these wires right here that I have running up zip tied to the frame up here, that's where the solar panels are going to plug in. There's 2 of them that go on top here and rest in these trays. And those are connected to the solar input here, and then we have the battery input in the middle, and then the load input on the far end. So the battery is going to connect right here, and then this wire here should go down and plug back in to the power distribution board down here. So on my solar airplanes, I do not run the motor off of the load output on the MPPT controller, because these these usually have low voltage protection where it cuts off the load when the battery gets below a certain voltage. And you don't want that on an airplane because you never want the battery to get cut off because then the plane will just crash. But on this, I will have low voltage cut off just to protect the battery. It's set really low. It's set to like, I don't know, probably 3 volts per cell, which is like already almost damaging the battery. But it'll just be one more stage of protection, just in case this voltage sensing relay Arduino controller doesn't do its job properly. And the cutoff voltage on this thing is a lot lower than this. So this should definitely trigger and stop the Rover well before this thing cuts off. But when this thing senses its low voltage threshold, it'll just stop the Rover from driving, but it'll still be in hold mode. So the flight controller and all the electronics will still be powered on.